Finding, sorting, data, multiple type returns, overloading, generics, and tuple unpacking. In this video, I will show you how to find and sort data using loops, as well as with find and sort procs, also generics, more overloading, with and without generics, and tuple unpacking. There is also a lot of cut content as an extra, which shows a lot more generics and overloading. The code for this video and its script documentation styled with nimip, as well as the cut content as an extra, is in the links in the description as a form of written tutorial. Multiple type arguments and returns. One can use the vertical bar line or the OR operator to specify that a proc can take or return multiple types of data. The OR operator is mostly used in conditional statements, e.g. if x or y. Use the vertical line for types. Here is an example of multiple types for an argument. So, the proc, data as string or integer, and the second proc, data as string or integer. The only difference is which one you use, preferably this one, the vertical line. Then we call them here and we get the output. And here is an example of multiple types for the return. So simply type 1 or the vertical line integer, and then you call it. Type 1 or type 2 approach problem. If we were to change the body of the above proc to say data plus data instead of data, we would get an error when the argument would be a string, as you cannot join strings with the plus operator. Variable types must be known at compile time. Therefore, you cannot use the vertical bar line or the OR operator to have a variable of multiple types. This does not compile. I have seen this approach be used here and there, and I do not agree with it because of the above problem. You can solve it by using some logic to check for type beforehand, but then the code would be doing extra work, wasting performance. So here are two solutions to this problem. The first solution is that it would be much better to simply overload the same proc so that you have two procs or more, one for each of the types, to achieve the same functionality with none of the problems. And solution 2 is generics. Using static for compile time multi-return. One can solve the above problem of the code appearing to be fine, but then failing at compilation or worse, sometime at runtime, by using static, then your data type for the argument. Static enforces that the value will be known at compile time. Therefore, we do not need to check for the types beforehand. Here is an example. So, proc test with excess static bool, a multi-return. Then we have to use the compile time if statement, which is when x hello, otherwise 101. So echo test true and echo test false will give us hello and 101 or 101. So if we don't use the static bool, this will then fail. The same example. Finding and sorting data. Finding the lowest number in a sequence. Here is my version of how to find the lowest integer value in a sequence. This example is as simple as this. Just make a variable with integer.high so that it's the highest value possible, so that the comparison will always be smaller. Then simply loop through the list you want and compare that the number in the sequence of list of numbers is smaller than the smallest number, and you will get it. Finding the lowest number in a sequence using min-max-index. Using min-max-index is as simple as the following. Simply call your container, and then in the square brackets for the index, you call your container again, and then .min-index or max-index, which will return the index of the smallest or the largest number it finds in that container. So minus 100 and 100 for the max. Sorting a sequence of integers. This is my example of how to sort a sequence of integers by their value descending. So first off, we start with a list of numbers, a sequence of integer. 0 is in here 3 times, because sorting a sequence with only a single occurrence of a number like 1 or 2 is very simple. But sorting a list that has any number of occurrences of a number like 0, which has 3 of any value, is much harder and more complex. And the minimum number of occurrences it has to work on is 3, at least my program. Now, the logic of this program is as follows. First loop will unwrap the list of numbers and get their index and number. Then the number will be checked that it's not in checked numbers, which is a hash set of type integer. The reason it's a hash set is because the max size of a normal set's integer is 16. And the other reason for a hash set is because we don't want duplicates in our checked numbers. And then we have another for loop. This one will be used so that when the iteration of the first one is 1, so that the second one will go through the entire list and check if any of the other elements are also 1 to be added to the list. And if another occurrence of number 1 or 2 is found in this list, then it will be put in the counted numbers. The number will be 1 or 2, and then the locations all the occurrences were found. And once this second loop finishes, the number we checked will be put in the checked numbers so that we don't check it again. This is to prevent that once the first for loop gets us to position of this 0, and it finds the second and the third and adds their occurrences, so that when the next iteration gets us to the second one, all of this doesn't repeat. This first line after the second for loop is so that the first loop hits, let's say 2, position 2, that the second loop doesn't check 2 against 2, but 2 against the following. Here is where the following happens. If the first loop gets us to here, and then we traverse using the second one forwards, so if 0 and the second one is also 0 and they're equal, we add 0 to the temporary and include 0 to the checked numbers list so that we're not going to check it again, and then we add both of them, both the indexes, into our temporary sequence. And then this second for loop will move us from this one all the way to the last 0, and it's also again going to add both of the indexes. This will get us into our temporary sequence 2 of this location, but we're going to solve this with a simple deduplication, which will happen over here. Once the second loop finishes, we come over here. This simply adds single occurrence numbers and their index into temporary num and sequence, while this for loop does for multiple. And then we deduplicate in case it's not a singular occurrence, and then we add it to the counted numbers with the number and their indexes of the occurrences. Then we display all the numbers and their occurrences. So first the original list, and then 1 gets index at 0, 2 is at index 1, 50 at 2, 100 is at 4 and 10, 0 is at 5, 9, and 11. Now this part will sort our counted numbers. So here we make a new variable, a tuple of type integer and sequence of type integer. So like our list counted numbers, which also has integer for the number and a sequence of locations. And then we set the first field to integer.high so that it is higher than all of the numbers in our counted numbers, so that when compared to the, let's say, the first one, number 1, will be smaller than the integer.high. Then we have variable SN location, as in smallest number location, which will be used to remove the smallest location from the counted number sequence, which is obviously not ordered. So the smallest number here is minus 100, so this one will be removed first, then minus 5, 0, and so on. Then we continue with a while loop, which will go for as long as counted numbers has any elements, till it's sorted. Then we reset the smallest number to the integer.high, so that once we find minus 100, which is the first one, so that the logic will not be if minus 5 is smaller than minus 100, which it is not, and thus our sorting would fail. And here we go through all of the elements of counted numbers. We use the pairs iterator so that we can use the SN location to capture the index of the smallest number that we will find, and the smallest number will be a tuple, so the number and its number of occurrences index, and then we delete the location. And then lastly, for every location in the smallest number 1 meaning the all of the occurrences indexes, so for, let's say, for number 0 we would have 3 occurrences, so for all 3 occurrences add to the sorted list all those 3 numbers, and then we end up with such a sorted list. So minus 100, minus 5, and then all the 3 zeros, 1, 2, and so on. As you can see, sorting a sequence of integers took quite a lot of code. Sorting a sequence of integers using sort. Sort is NIM's default sorting algorithm function. Just by the look of it, you can see that this code is much shorter and simpler than the one without using sort. So all we have to do is call the sort func on our sorted list of numbers, and we get the result, which is from lowest to highest, ascending. And here is a descending sort example. So when calling the .sort on our list of numbers, we set the order to sort order .descending. Now sort proc modifies the existing variable and uses the system.cmp compare for comparisons by default. There is also the sorted proc, which returns a new copy instead of modifying the existing container. Here's an example with echo. We simply call .sorted on our list, and echo will take that new list and display it, not change the original. You can also specify which comparison CMP proc to use, like this. Sort it, and then system.cmp, and the type you want. You can replace that CMP compare proc with one of the following from the NIM standard library's docs search results. Generics. Generics in NIM are used to parameterize procs, iterators, or types with type parameters. Square brackets are used along with capital letters inside of them, separated by commas after a type's name, proc, or iterator to tell the compiler that this will be a generic. So, generic with T inside of square brackets, or another letter. The above examples are incomplete. They will not work just yet. Again, using the square brackets with a capital letter inside, we'll just mark the type proc iterator as a generic. Now we're required to use that T, can be any capital letter, in the arguments of the proc iterator and on the fields of a type. Generic definitions. So, data as string now becomes data as T, the keyword used in the object. And here is a example for a tuple. Can be also used for an object. So 2 keywords, A and B in square brackets, and then we use them for the field names. Name as A and age as B. And then for a proc generic proc, and then square brackets t before the parameters, and then the parameter of any type or whatever you want to call it as t. And then for the iterator goes the same, and you can also use it for the return type. And lastly, for a proc, using a container for its type, so sequence t instead of integer, string, etc. Generic object initialization. So for an example, we're going to use this definition of an object, and here is the initialization. So generic object, instead of t, you can put whatever data type you want, so string, and then give it the value, a string, and then the second example, generic object as integer, and data as 101. And here we echo the types to confirm what they are. So data is of type generic object, system.string, and for the second one, system.integer. System meaning the by default imported module from where the integer type comes from. Generic tuple initialization. Calling generic procs and iterators is exactly the same as non-generic versions, unlike structures like objects and tuples, the initialization part. More overloading. To demonstrate and teach you more about overloading, we're going to overload the find proc. The find proc from the strudels module, string utilities, which is also in some other modules, is very useful for finding substrings, a part of a string, in a string. In fact, we have already used it in both the sets and the hash sets videos in order to find and remove specified separators from a string. This time though, we're going to use the system.find version, which does not deal with strings, but with an element of some type, using find with a sequence of numbers. So here is an example sequence, and here we use the find -10, and it's founded at index 3, so 0, 1, 2, and 3. If we were to reinsert the index back, we would get the -10. So let location is my sequence.find -10, and then we reinsert the location and we get -10. Using find with a sequence of objects. So here is our definition for some object, name and age. Here we make a new sequence of type SomeObject, add two SomeObjects into it, and then we make a new variable of let type womprat and find womprat inside our sequence, and then display that with reinsertion, but we get an error. This is the error message we get for trying to use the find proc on our SomeObject. The error message might be a bit misleading. Here it's saying proc =, for comparison, but the errors comes from the find proc because it doesn't know our SomeObject and it doesn't work on objects. But the =, does, as you can see here below. It doesn't matter what our object is called, in our case SomeObject, this will work with it, unless it's a bit too complex for the =, to work with. Again, this might look a bit misleading since the find proc is not being shown here in the error message, but the find proc is using this =, to match what it finds against one of these types, and then returning bool, true or false, whether it finds it or not. Overloading find proc. In order for our SomeObject to work with the above code, we need to overload the find proc for our custom object. But first off, here is how the system.findProc is defined, a generic. So proc find along with the export symbol so that it can be used outside of this module, when imported. TS for two generic keywords, AST and item SS. Return type of integer, and then inline pragma, which means that this proc should not be called like this, find, and then in parentheses something to find, but instead some value dot find. But it will work in either way. Now the body, result as 0, since all containers and strings start with 0. Then for every item in A, which could also be called as a.items, or not at all, since the items iterator is used by default implicitly. And then if what we're searching for is found, return, and then increment the result so that we move with the index. This could have been on the other line over here, indented as well. And -1 if it doesn't find anything. And here is the body of my overload in order to find by the fields of our SumObject. Now, since we already know where we are going to be looking for our data, sequence of SumObject, we don't need this to be a generic type. Now, result is still at 0 and -1, so that it starts at 0 and returns -1 if it fails. Now, instead of using the items iterator, we use the pairs iterator instead, so that we get the element, our SumObject, and the index of it inside the sequence. And here we are comparing the fields of our SumObject against the item we are looking for. Now, both of them have to be in string, because if we try to compare, for example, integer against some other data type like float, it will crash. Wrong data types to be compared. But if we use strings, then we are comparing a string against a string, and if the contents are different, well, they're just different, no problem here. And now we use our overloaded find again, pretty much the same code as above. Let wompret sequence of SumObject.find wompret, and then display at which index, and then the reinsertion. So found name wompret at index 1, and the reinsertion is wompret h5. And then for the h field, since we're using a generic, we can simply put any data type we want. So instead of wompret, a string, an integer, 5, and it finds it. And reinsertion. Square brackets overload for ease of life. Square brackets overload will allow us to replace the sequence of SumObject.find wompret to sequence of SumObject square brackets wompret to get the index. The overload is mostly the same as the find overload, except that the item argument is now a string instead of a generic. This is because if the overloaded square brackets was given an integer, it would still try to return us the element at the index of that integer. And in this instance, 5 is not in the index of the two fields, 0, 1, resulting in an error. So here are all the changes. And the first line is trying to parse the stringified field if it's an integer, and if it is, then we compare it against the item that we're looking for and return the index if yes. If the parsing fails, then that means it's probably a string in our case. So string against string. But we still have to use the dollar symbol because it could receive something else. And the NIMS extension for Visual Studio Code complains about it, and if you try to compile, it will also crash without it. Now, here is an example of how to use it. So, instead of using the find proc, we simply use the square brackets for our string version. Now, the following example for the h field will crash if the item argument is a generic, because trying to use 5 in square brackets will automatically go to try to access the index at that location of our sequence of SumObject. Instead of trying to find the number 5 we overloaded the square brackets with, and so we will get an error of index out of bounds. Not here yet, but over here. The only thing we can do about it is to make that number 5 into a string version. So with a dollar, $5. And now it works. Tuple unpacking. In the past video of NIM for Beginners, number 14, tuples, I have shown you tuples. Now it's time to explain and demonstrate tuple unpacking. Tuple unpacking is quite simple. You can use them to give values, assignment, to multiple variables, var, constants, const, or immutable variables, let, at once. And here is an example. Let, in parentheses, v1, c1, l1, and then assign to them var, const, and let, in parentheses, because this is a tuple. And it works. All of the following is treated as syntactic sugar for basically the following code of example 1. I don't think I have ever shown this before, but yes, you can access any field of a tuple without knowing the name of the field, especially useful for anonymous tuples like here, fields without names. I do recommend though that you do use the names of the fields over the index when the names are present. When tuple unpacking tuples with numbers, literals, into var and let variables, they get assigned their values without a temporary tuple. Since you can nest any container within another container, array, sequence, set, table, etc., as well as data structures in a data structure, object tuple, you can also use nested tuples for tuple unpacking. Tuple unpacking use case. In NIM, you can have multiple return types for a proc by using object variants and union types, integer, vertical bar, string. This can also be achieved by using tuples. But tuples don't just allow for multiple types to be returned, they allow for multiple returns, which can then easily be unpacked into variables and containers. Here is an example of a multiple return. So, the return type, a tuple that has integer and then a nested tuple, then 2 more integers, and then an example return. And then the tuple unpacking with this pattern of a tuple inside a tuple. Another very useful part of tuple unpacking is that you don't need to return anything. 1, 2, all, or none. Okay, that's it for this video. Thanks for watching. Like, share, and subscribe, as well as click the bell icon if you liked it. And one more. You can also support me on Patreon. If you had any problems with any part of the video, let me know in the comment section. The code of this video, script, and documentation are in the link in the description as a form of written tutorial. Have fun.